Assalamualaikum and hi everyone. In this video, we're going to explain to you guys about the second law of thermodynamics, the thermal energy reservoirs, and also the Carnot refrigerator and heat pump. However, before we jump into this topic, let's recall on what we have learned before. So, what is the first law of thermodynamics? So far in this course, we've been analyzing most of our thermodynamics processes and devices by using the conservation of energy equation, otherwise known as first law of thermodynamics. It is reasonable to conclude that a process must satisfy the first law to occur. For example, a cup of coffee left in a cooler room eventually cools off. This process must satisfy the first law of thermodynamics, since the amount of energy is lost by the coffee is equal to the amount gained by the surrounding air. We all know that the reverse process will never take place, yet it would not violate the first law if doing so, as long as the amount of energy lost in the air is equal to the amount gained by the coffee.
The first law of thermodynamics doesn't guarantee a process existence, but is improved by the introduction of the second law. The reverse process violates the second law of thermodynamics that is easily detected with the help of a property called entropy, a process that cannot occur unless it satisfies both the first and the second laws of thermodynamics that we'll define in Chapter 7. It restricts our analysis of the energy conservation by telling us that a natural process can only occur in a certain direction and not in reverse direction. The second law focuses on determining the quality and degree of degradation of energy, while the first law focuses on its quantity and transformation. The second law of thermodynamics is utilized to determine theoretical limits for engineering systems like heat engines and refrigerators, and predict the completion of chemical reactions.
The second law of thermodynamics uses a hypothetical body with large thermal energy capacity, known as a thermal energy reservoir, which can supply or absorb finite amounts of heat without temperature change. To have an idea, for example, in this picture, large bodies of water such as oceans, lakes, and rivers, as well as the atmospheric air, can be modeled accurately as thermal energy reservoirs because of their large thermal energy storage capabilities or thermal masses. Reservoir that supplies energy in the form of heat is called a source, and one that absorbs energy in the form of heat is called a sink, as shown in this picture. Thermal energy reservoirs are often referred to as heat reservoirs since they supply or absorb energy in the form of heat.
Now, I will explain about the Carnot refrigerator and heat pump. Before we start, I will briefly explain about how refrigerators function. We know from our day-to-day interactions that heat is transferred in the direction of decreasing temperature. So, if we have a hot cup of soup, it decreases in temperature until it's room temperature. This happens naturally without us having to do anything. However, if we wanted to transfer more heat from our soup to below room temperature, we need special devices. In other words, to transfer heat from a low temperature medium to a high temperature medium requires devices called refrigerators. So imagine you're inside your room on a hot summer day and the inside temperature is 25 degrees Celsius. It is too hot, so you turn on the air conditioner. What it's doing is absorbing the heat from the room air and discharging it to the outside. In simple terms, it's moving heat away from your room and taking it to another location. The key here is to understand that the outside temperature is usually higher than the room temperature. So, it moves heat from a low temperature medium to a high temperature medium. Next, I will move to our main topic, which is the Carnot refrigerator and heat pump. A refrigerator or a heat pump that operates on the reverse Carnot cycle is called a Carnot refrigerator or a Carnot heat pump. The coefficient of performance of any refrigerator or heat pump, either reversible or irreversible, is given by this equation, where QL is the amount of heat absorbed from the low temperature medium and QH is the amount of heat rejected to the high temperature medium. The coefficient of performance of all reversible refrigerators or heat pumps can be determined by replacing the heat transfer ratios in the preceding relations with the ratios of the absolute temperatures of the high and low temperature reservoirs, as expressed by the equation QH over QL in reverse is equals to TH over TL. Then, the coefficient of performance relations for reversible refrigerators and heat pumps will become as shown. These are the highest coefficients of performance that a refrigerator or a heat pump operating within the temperature limits of TL and TH can have. All actual refrigerators or heat pumps operating within these temperature limits TL and TH have lower coefficients of performance. So for example 6.6, a Carnot refrigeration cycle operating in the saturation dome. So the question asks, a Carnot refrigeration cycle is executed in a closed system in the saturated liquid vapor mixture region using 0.8 kg of refrigerant 134A as the working fluid figure as shown in figure 6.5.1. So the maximum and the minimum temperatures in the cycle are 20 and -8 degrees Celsius respectively. It is known that the refrigerant is saturated liquid at the end of the heat rejection process, and the net work input to the cycle is 15 kJ. So, by determining the fraction of the mass of the refrigerant that vaporizes during the heat addition process and the pressure at the end of the heat rejection process. So, the question asks for the fraction of mass of refrigerant that vaporizes during heat addition process and pressure at the end of the heat rejection process. So, we will be using the mass fraction equal to m mass evaporation over mass total. So we list out the information given, which is m total equal to 0.8 kg, and TH is 20 degrees Celsius, TL is -8 degrees Celsius, with work input is 15 kJ. So first we need to find QL of the mass the refrigerant vaporized. Okay, so then we need to use the equation coefficient of performance for refrigerator, which is equals to 1 over TH over TL minus 1. So we substitute the value of 20 and -8, then we plus with 273 Kelvin, convert it to Kelvin, then we minus with 1, then we get the value 9.464. So we substitute the value of COP for R that we got in the equation QL equals to COP of R times weight work input. So 6.464, we times weight work input 15 kJ, we got 142 kJ. Then we'll be using table A11 to find the enthalpy of evaporation of R. For us to substitute in the equation M evaporation equals to QL over HFG. So, by the equation above, we know that the enthalpy of evaporation of R at region 134A is at -8 degrees Celsius. So, for the HFG, enthalpy of FG, we get the value of 204.59 kilojoule per kilogram. So from the value that we got in table A11, we substitute it in the equation of M evaporation. So 142 kilojoule of QL we get from above. Here, we substitute it and we overrate with 204.59, the value we get from table A11. And we get the answer of 0.694 kilogram. Then we substitute the value of mass evaporation over with the mass total. Mass total given is 0.8 kilogram. So 0.694 kilogram is over with 0.8 kilogram. We get the mass fraction is 0.868 or 86.8%. Then it also asks of the pressure at the end of the heat rejection process. at the end of heat rejection process, we have process 1, process 2, process 3, and process 4. So we have to find the pressure at 4 here. So by using table of A11 again, we know that the P saturated is at 20 degrees Celsius from the question above. So the highest point of pressure is at 20 degrees Celsius. So we take the value of pressure at 20 degrees Celsius in A11. So from here, at 20 degrees Celsius, the pressure we get is 572.07. So that is the value we get for pressure at 4, which is 572.07 kilopascal. That's all from me. Thank you.
Just now, Dina has explained the formula to get the highest coefficient of performance of the Carnot refrigerator and heat pump between TL and H. However, all actual refrigerator and heat pump have lower coefficient of performance. The COP of reversible or Carnot refrigerator or heat pump is a maximum theoretical value for the specified temperature limits. For further understanding of the Carnot refrigerator and heat pump, let us try some example question. In this question, it is all about the Carnot heat pump. We have to determine the minimum power required to drive the heat pump. As we know, we have to maintain the 21 degrees Celsius in the house, and the outside temperature is negative 5 degrees Celsius, and the heat loss rate is 37.5 kilowatt. First of all, we have to find the coefficient of performance of the heat pump by using this formula. And then we substitute the value given in the formula, and then we got the coefficient of performance is 11.3. And then we now can find the required power input with the formula given, which is QH over COPH. We substitute the value, which is 37.5 kilowatt over 11.3, and then the answer is 3.32 kilowatt. And this is the power required to maintain the temperature of 21 degrees Celsius by the heat pump.